Hello and welcome to the walkthrough of the August 2015 New York State Regents Chemistry Exam Part B-2. This is the pre-response section of the Regents exam, and we're going to be starting with question number 51. Question 51. Determine the vapor pressure of ethanol at 90 degrees Celsius. To do this, we need to look up the vapor pressure of ethanol at 90 degrees Celsius using Table H. So we'll bring in a section of the reference tables. This is Table H. We're looking for ethanol, so we're going to focus on this part of the graph, the ethanol portion of the graph. We're going to find 90 degrees Celsius. Be careful with this x-axis because it goes in 5-degree increments. So we have 75, and there's 80, 85, and 90. So we trace up 90 degrees all the way up to where the intersection of the ethanol curve is and go across to find the vapor pressure in kilopascals. It's 150 kilopascals. So our answer to question 51 is 150 kilopascals. You can see the answer booklet will already have the units in place for you. Question 52. Explain in terms of particle arrangement why a sample of solid sodium chloride has less entropy than a sample of aqueous sodium chloride. Make sure in these types of questions, if they give you terms to use in your answer, take advantage of that, and please do use those terms. Now, we know that entropy deals with the randomness of the particles. Entropy is about randomness. And you should recall that solids have the least amount of randomness, and gases have the most. So our answer to this one we can structure by saying particles in the solid sodium chloride are arranged, or we're going to go with less randomly. That would be a perfectly sufficient answer. There are other ways that you could answer this that would be correct, but this is a very direct answer. It gets right to the point. Question 53. Determine the molecular formula for a compound that has the empirical formula CH2O and a molar mass of 120 grams per mole. This is an empirical versus molecular formula question. So I like to set up a little chart where we're going to compare empirical values with molecular values, considering the formula and mass involved. In the question, you are given the empirical formula of CH2O. So we're going to enter that in our little chart. And you are told that the molecular mass, the molar mass of the molecular formula is 120 grams per mole. So that goes with the molecular. So our task is to find out how much bigger is the molecular formula than the empirical. It's going to be some multiple of whatever the empirical formula is. To figure that out, we can concentrate on the mass value. So first we're going to calculate the mass of CH2O. Carbon supplies a mass of 12. There's 2 hydrogens, at 1 each is 2, and the oxygen is 16. So we have a grand total here of 34. So the question is, how many times does 34 go into 120? And when you figure that out, you'll see that it's going to be 4 times. And that means that our molecular formula is going to be 4 times as large as the empirical formula. So we have to increase everything by a factor of 4. So our molecular formula has to have 4 carbons, 4 times 2, or 8 hydrogens, and we're going to have 4 oxygens, O4. So the molecular formula that will have a formula mass of 120 has to be C4, H8, O4. Question 54. A student drew the Lewis electron dot diagram below to represent sodium chloride. Here's a student's representation of sodium chloride. Explain why this diagram is not an accurate representation for the bonding in sodium chloride. I think the best approach to understanding what's going on here is first, let's figure out what kind of bond should be existing between sodium and chlorine. So we're going to use electronegativity values to determine that pretty quickly. I've looked up the electronegativity values of sodium, it's 0.9. and chlorine 3.2. You can see that the difference between these two values is actually 2.3. This is a very high electronegativity difference, indicating that the bond between sodium and chlorine should be an ionic bond. Well, your student has drawn in their picture a molecular substance. It's showing the sharing of 2 electrons. This is a molecular structure, so we could just say that the student has drawn a molecular substance and sodium chloride is actually an ionic substance. Put in other words, the diagram does not show electron transfer, or ions. And this is an ionic compound. It should have ions, and you would have to represent the electron transfer somehow. So many different ways it can be stated, and the Regents will gladly accept any accurate explanation of why this diagram is wrong, and here are just a few. Question 55. Given the formula for heptanal, and they have a big giant formula here, it's a structural formula of an organic compound, so you would think at first glance this is an organic chemistry question, and it is, but look at what they're asking. Determine the gram formula mass of heptanal. So we really have to add up the masses of all these individual atoms. So this is really a mathematics of formulas and equations question. We're calculating a gram formula mass. I put together a list of all the atoms that are present in this structure, and we have to count them up and then multiply them by their formula masses as derived from the periodic table, and then we can get a grand total. So first the carbons. We see there's a total of 7 carbons in the structure. They each have a mass of 12, so 7 times 12 is 84. There's only one oxygen atom that has a mass of 16, and you count up all your little hydrogens, you're going to see there's a total of 14 of those. They each weigh 1, so it's a grand total of 14. We add everything up, we get 114 as our total. So the gram formula mass of this structure is 114 grams per mole. The answer booklet has given you the units, so you don't have to be concerned with that. Question 56. Compare the mass of a proton to the mass of an electron. They're only saying compare. You don't have to be too critical here. You don't have to get into the numbers involved. But you do have to know your subatomic particles pretty well. So the only reference in the reference table that might give you this is the symbols used in nuclear chemistry. They do have the proton, and the beta particle is our representation of an electron. And you can see the electron, the proton symbols here. The electron has virtually no mass when compared to the proton. In fact, the electron is usually considered to be about 1/1800th the size of a proton. So how do we put this into simple words? Well, let's keep it really simple. The proton has more mass than the electron. You could also say the electron has less mass than the proton. Say it any way you want, but we don't even have to be numerical here. We're just going to say which one is larger. Question 57. In nature, 1.07% of the atoms in a carbon sample are made of carbon-13. In the space in your answer booklet, show only the numerical setup. You don't have to do the calculation, where you calculate the number of carbon-13 atoms in a sample that contains 3.28 times 10 to the 24th atoms of carbon. Well, this is a standard percentage problem right out of math class. We want to know what number is 1.07% of the total, 3.28 times 10 to the 24th. So I'm going to use a really simple technique. I'm going to take that total number, 3.28 times 10 to the 24th, and I'm going to multiply it by the decimal equivalent of the percentage, 1.07, decimal equivalent being 0.0107. I'm going to stop right there because they only wanted the numerical setup. They don't want the answer. So this is a perfectly legitimate answer. There are other ways mathematically to represent this calculation. Any way that would lead to the correct calculation is going to be accepted. And now we enter the part of the Regents exam where questions are grouped together. The first group of questions we encounter are questions 58 and 59, and they're going to share some common information in their narrative. In this case, a heating curve is provided. And there are 2 questions based on the heating curve, and I've scanned through this just to figure out what kind of skills are going to be necessary. For the first question, number 58, you're going to have to read and interpret the heating curve. And in question 59, you're going to be explaining the potential energy change that happens during a phase change. So let's take a look at question number 58. In question 58, we're asked to determine the boiling point of the sample at standard pressure. Now on a heating curve, the boiling point occurs when you go from the liquid phase to the gas phase. And the narrative explains that the first segment, A to B here, are substances in the liquid phase, and the second segment is the gas phase. So the flat portion of this graph is the phase change between liquid and gas, and that occurs at the boiling point. So all we have to do here is read the graph, and that transition between liquid and gas occurs at a temperature of 95 degrees Celsius, and that's your answer to question 58. Question 59. State what happens to the potential energy of the particles of the sample during time interval B to C. On the graph, the time interval from B to C is that part of the graph where a phase change is occurring. And during phase changes, the kinetic energy stays the same. We know this because kinetic energy is a measure that is associated with the temperature being the average kinetic energy of the particles in a substance. And since that's not changing, the kinetic energy is staying the same. So all the energy that's being put into this sample is being used to change the phase and increase the potential energy. So our potential energy during the flat section of this graph, the phase change, is an increase. Potential energy increases during the segment BC interval. Next up is grouped questions 60 and 61. They come together with the narrative. A sample of nitric acid contains both H3O plus ions and NO3 minus ions, and the sample has a pH of 1. So we're into acids and bases now. The two things we're going to be asked to do are to work with the definition of areneous acids and also use the acid-base indicator chart, Table M, to answer a question related to the pH. Question number 60. Write a name of the positive ion present in this sample. They couldn't have made this too much easier. They've given us the positive ion's identity right here, H3O+. So we can simply go to Table E, the table of selected polyatomic ions, find H3O+, read its name, and then transfer its name to our answer space, and we'd be perfectly correct. It's the hydronium ion. And question 61, what is the color of methyl orange after it is added to this sample? Now, they don't tell you where to look, but you need to be aware that there is a table in your reference table. It's called Table M, which gives you the color coding associated with pH values for various indicators, methyl orange being one of those indicators. So what we need to do to answer this question is to look up the pH value, which in this case is the number 1, on Table M. So for methyl orange, if the pH is 1, you can see the color range indicated here is 3.1 to 4.4. So anything less than 3.1 is going to give us a red color. So this indicator is going to be extremely red because the pH is less than the lower part of the range of 3.1. So the answer to this question is the word red. And the final group of questions in part B2 for this exam, 62 through 65, all based on the narrative, is showing a fission reaction for uranium-235. Here's the nuclear equation for that fission reaction. It's already balanced for you. It's all written out. And a little bit of explanation. Both radioisotopes produced by this fission reaction undergo beta decay. So they're telling us that the xenon and the strontium are both beta decay. And they give you the half-life for xenon 140 as 13.6 seconds and the half-life of strontium as 1.25 minutes. So they've given us half-life information and the equation for the fission. The four things we're going to have to do with this: first of all, we're going to get into the definition of nuclear fission. We're going to have to write a small nuclear equation. We have to do a half-life calculation, and we also have to do a descriptive narrative here about the behavior of nuclear emissions. Question 62. Explain in terms of both reactants and products why the reaction represented by the nuclear equation is a fission reaction. So we have to mention something from the left side of the equation and something about what's going on the right side of the equation. Getting to the definition of what fission really is, fission involves the splitting of a large nucleus to form two smaller nuclei. And that's clearly what's going on here. We have the large nuclei, uranium-235, which is being split through the collision with this neutron to form two smaller nuclei, the xenon and the strontium nuclei. So, in simplest terms, we could say the U-235 atom is split into two smaller atoms. So we've referred to something from the left side and something from the right side to answer the question in the context of fission. Question 63. Complete the equation in your answer booklet for the decay of xenon 140 by writing a notation for the missing product. So this is the completion of a nuclear equation, and they've written everything out for you in the answer booklet. You only have to identify what the other missing piece is. To do this kind of question, we have to consider both the mass and the charge involved. So first, from the mass perspective, we start with a mass of 140, and we're going to release a particle that has no mass and another particle that has a mass of, well, if we're conserving the mass, that 140 if we've taken nothing away from it, we still have 140. So the top part of our formula is going to be 140. The mass is 140. On the bottom part, we start with 54. We take away -1. So we're subtracting -1. So our atomic number is actually going to go up by 1. It's going to be a 55. So we have the numerical data, 140 over 55. Now to identify what that particle is, we'll use the atomic number. We'll refer to the periodic table. We'll look up element number 55, which you can see here is cesium. And we'll come back and finish our answer by putting CS for cesium. This is a cesium 140 over 55. Question 64. Determine the time required for an original 24-gram sample of strontium-94 to decay until only 1.5 grams of the sample remains unchanged. So here we know what the final mass is supposed to be. We know what the initial mass is supposed to be. We also know that your strontium-94 has a half-life of 1.25 minutes. The other information is not necessary because we're only looking at the strontium here. Now, half-life problems can be solved very directly by a series of sort of complicated formulas, but you can kind of skip past all that because for Regents chemistry, the simplicity of a little chart would be very helpful here. A chart that keeps track of the amounts of substance present and the fractions that remain. If we start off our problem with the full sample of 24 grams, and that is at time 0 where no half-lives have happened yet, and the fraction of our sample is a full sample of 1. Now if we start cutting this number in half, we can see how many times we'll have to cut this number in half to get down to what the question suggested, which is the 1.5 grams. So let's start with 24 and start cutting it in half. After the first half-life, we'll be down to 12. Second half-life will take us in half again to a 6. The third half-life takes us to a 3. And the fourth half-life will take us to our desired value of 1.5. So after not 1, not 2, not 3, but 4 half-lives, we'll have our desired final mass of 1.5 grams. So it takes 4 half-lives for this to occur. 4 half-lives, since they each take 1.25 minutes, we multiply that number by 4, and we'll get our answer, which is going to be a grand total of 5 minutes. And our final question on this part, number 65, on the diagram in the answer booklet, draw an arrow to represent the path of an emitted beta particle in the electric field between two oppositely charged metal plates. Key things you have to know here, first of all, are what are the charge of a beta particle, and what will be the behavior of that beta particle in an electric field. And that's governed by the idea that opposites attract and like charges repel. So our beta particle, which has the negative charge, as it is projected through this field, is going to be drawn toward the positive plate and away from the negative plate. So it's going to bend to the left as it goes through this field. So we could draw our arrow this way and have a solid line, draw whatever type of line you want, but you have to make sure that you show it curving upward or toward the positively charged plate. And that wraps it up for part B-2 of the August 2015 New York State Chemistry Regents exam. Be sure to search through the web page that you're on right now and try to find the remaining parts of this exam. And thank you for watching. If you have any questions, comments, or would like to get permission to use more materials from my website, you can email me at asnyder@alchemtutor.com or visit the website alchemtutor.com.